welcome to the second lecture of chapter 4. Today we're going to talk about some equilibrium constant for describing the redox reaction. So what we did for half reaction in the previous lecture, talking about non-standard condition. And also talking about whether a process is spontaneous. So two things we need to focus on. Half reaction versus redox reaction, which is basically a combination of the two reactions. And also standard condition versus non-standard condition. So these two we're going to cover in this lecture. So just keep in mind whether we're talking about half reaction, standard, non-standard, redox reaction, standard, non-standard. So quickly, what we did in the previous lecture was only one category. We talked about half reaction at standard condition. So overall, first we started with describing a redox reaction, or like a half reaction, to be basically a reaction that includes that electron that we talked about. And this could be, if we go in this way, this would be a reduction. And if we go in that way, this would be oxidation. And also we mentioned that basically a redox reaction is a combination of two of these guys, two half reactions. One serve as the reduction, one serves as the oxidation. And then we describe also the K value for this reaction, like any other K values. So this one basically the product over the reactant. And then we also mentioned that we could basically rearrange it to mention that this could be, or the ratio of the reduced species to the oxidized species basically can be changed by changing the activity of electron. So we can change this by changing the activity of electron. So this was a general description of what we had for a general half reaction, combining two of them, a general redox reaction. And we specifically focus on a half reaction at standard condition. And we use that special designation. The standard reaction was first written in the oxidation form and also releasing one electron. So 1n of reduced species producing 1n of the oxidized species plus only one electron. So it's releasing electron and only one electron. And if that's the case, that K value this time for this specific reaction, we use special designation of E0, E0, that we can find from table. And then this was basically ox over 1n, the activity of electron. And then so we call this basically the standard electron activity. And we use basically PE0 also to be minus log of E0. So again, we cover only one condition, half reaction at the standard condition. So the next step, we want to look at a redox reaction at the standard condition. At the end of the lecture, half reaction and redox at non-standard condition by introducing Nernst equation. So now let's see what happens if we move on to the standard reaction and what would be the E0 for that standard reaction. So the very important note here is that the standard reaction is the one that is a combination of two standard half reactions. So that's very important. So again, standard reaction is formed by combining two standard half reactions. And now we want to see how the equilibrium constant of the redox reaction at standard condition is related to the the standard of half reactions. So basically what we're looking for. So let's assume this very general notation for the oxidation and reduction reaction. So oxidation, let's assume this is basically A forming B plus N1 electron. So the standard notation for this half reaction would be 1 over N1 A forming 1 over N1 B plus electron. And for this specific reaction, the K value would be equal to E0 of oxidation. We do the same thing for reduction. Let's assume we have this general form of reduction that D plus N2 electron is forming C. And first, in order to write the standard notation, first we need to make it in the oxidation form and releasing only one electron. So this would be 1 over N2C forming 1 over N2D plus 1 electron. And this would be E0 of reduced. So now we know that based on these two half reactions, we can make a redox reaction in which A is oxidized to B and D is reduced to C. But in order to write the standard half reactions or the standard overall reaction, we have to combine the two standard half reactions. So basically what we need to do is to form the overall redox reaction to be, which is reaction 1 plus the reverse of reaction 2. And if we do that, this would be 1 over N1 A plus 1 over N2 D, which would give us 1 over N1 B plus 1 over N2 C. And now this is basically a standard redox reaction. Why standard? Because it's coming from two standard half reactions. So that's very, very important. And now the K value for this reaction would be the standard electron activity of the reaction. And since we can make this overall reactions from these two reactions, we know how to use the K value of individual. So then the K, which is E0 of reaction, would be the K of the first reaction times 1 over the K of the second reaction. Or we could do minus log PE0 of reaction is equal to PE0 of oxidation minus PE0 of reduction. So if you took other electrochemical courses, you've seen this form probably, but in different notations. Specifically E0, the capital E, representing the standard reduction voltage. But this is basically the same thing. We're approaching it from the electron activity at the standard condition. So now we know how to calculate for redox reaction based on the half reactions at standard condition. But the key point is, if we're using directly this formula, we have to make sure the overall reaction, the redox reaction, is coming from two half reactions that are at standard condition, written in the standard notation. So now we can do a very quick practice to see that whether we're allowed to use that formula directly or we need to basically derive the K value from what we've learned in chapter 1. So now we have reaction A. 1/8 of H2S is with HOCl, forming Cl minus, and sulfate and hydrogen and proton. It looks like it's coming from a standard half reaction because of those weird values in front of each element, each compound. But just to make sure, we want to basically confirm that is coming from a two standard half reaction. And you'll be given this sort of information a lot. So what it says here that H2S is in one half reaction with sulfate. So in one half reaction, you have H2S and sulfate. The other half reaction, you have HOCl and Cl minus. So that's the kind of information that is related to the first one. So now we want to do decouple the first reaction into two reactions and see if whether that one is a standard redox reaction. First, we need to identify whether H2SSO4 was a part of reduction or oxidation. The easiest way to do it is probably looking at the oxidation state of Cl in the second part. So for part A, we look at the oxidation state of Cl. So one in HOCl, one in Cl minus. So we know Cl is a part of the product. So the oxidation state of Cl minus is basically -1. So it's -1. And then on the other side of the reaction, this would be HOCl. We know H is +1, O is -2, and the overall must be 0. So that means, what's the value for Cl? +1. It has to be +1. So overall, we have sum of oxidation state of 0. So it's going from +1 to -1. That means it's been oxidized. So the oxidation state went down. Or sorry, opposite. So it's been reduced. So that means the oxidation reaction involves the other two pairs, these two pairs. So we got H2S in one hand, and then we have SO4 2- on the other hand. And we basically now know how to balance a redox reaction based on what we've learned in the previous lecture. So then this would be +4 water. On the other side, we got 10 proton and 8 electron. So we don't have any K value representing this specific reaction, but we know we have E0 that represent the standard notation for this reaction. So we can basically make it divided by 8. So 1/8 of H2S plus 1/2 of water is forming basically 1/8 of sulfate plus 5/4 of H plus electron. So then this would be, then we are allowed to use that E0. And then this would be E0 of H2S and sulfate. So obviously, if this is the oxidation reaction, the other pair would be involved in the reduction reaction. So then it would be pair of HOCl and Cl minus. Again, if we balance this reaction, eventually this would be something like this. And H plus 2 electron. Standard notation, first we need to make it oxidative and then dividing it by 2. So 1/2 of Cl minus plus half of water. Then it would be half of HOCl, half of proton, then 1 electron. Then E0 would be basically E0 of HOCl and Cl minus. And now we can write down the overall reaction. Which would be basically, let's call this 1 and 2. Similar to the previous case, reaction 1 plus reverse of reaction 2. Then we get 1/8 H2S plus half of HOCl, half of Cl minus, plus 1/8 of sulfate, plus 3/4 of H plus. So basically what we're doing here is checking whether the reaction we make from the combined standard reaction would be the same as what we had in part A. Is it the same? It is? Yeah. So it's exactly the same. So the reaction that is given, the redox reaction that is given in part A is coming directly from 2 standard half reactions. So now we can basically calculate the K value. K value would be in this case equal to the E0 of reaction. And based on what we've learned in the previous page, PE0 of reaction would be PE0 of oxidation minus PE0 of the reduction. What would be the value then? What's that? So what's the oxidation? Mm-hmm. Oh, that's the reduction, right? So the pair that is in the oxidation is basically the H2S pair. Oh, wait. Just to double check. Okay, yeah, you're right. So this would be the oxidation would be 5.08 minus the 1,4 reduction, 25.10. or this would be basically minus 20.02. So again, we could calculate this based on the K values if it was given, or like the K value for the, but this one, because it's standard, then we can basically quickly calculate it using the formula we had. Okay, now let's look at part B. Part B is the specific reaction. It doesn't look like a standard reaction because we have some other values like 2 that probably is not coming from a half reaction, 2 standard half reaction. So we can go quickly do part B. So it's not standard. We can actually show that by driving the standard reactions and then combining the two and see, oh, this is not this exact reaction that is given. So to do that, we just need to play with it using the information we learned in chapter 1 and then combine the K or E0 values to get to the K value for the specific reaction. Again, first we need to know what is reduced, what is oxidized. It seems in one pair we have ammonia and nitrate, and on the other one we have oxygen and water. So we have ammonia and nitrate. So quickly we can look at the nitrogen oxidation state to identify whether this was oxidation or reduction. So this would be the oxidation state of nitrogen. We can quickly calculate that. In ammonia, H plus is always +1, so it has to be -3. On the other side, we know oxygen is always -2, so that would be 3 times -2. Overall charge is -1, so it has to be +5. So it's increased, so that means ammonia was a part of the oxidation reaction. So this would be our oxidation reaction. And when we balance this reaction, this would be 3 water. And on the other side, this would be a 9H plus 8 electron. But obviously, we don't have any information about this specific reaction. Yeah. And but we need to basically write it in a way that we have the information about this reaction, and that's basically the standard notation. So this would be 1/8 of ammonia plus 3/8 of water, giving us 1/8 of nitrate plus 9/8 of proton plus electron. And now for this specific reaction, we have the K value, which is basically E0 of ammonia nitrate. So we can do the same thing for the other side of the reaction, the reduction. So just for the sake of time, I quickly balance the reaction. It would be O2 plus 4 hydrogen plus 4 electron to give us 2 water. And then the standard would be half of water would give us 1/4 of oxygen plus proton plus electron. And the E0 would be basically for 1, O2 and H2O. So now the question is, how do we make reaction in part B from these two reactions that we have information about? So the other case was very simple. So it was just one plus the reverse of the other one. How about now? How do we generate the overall reaction? Exactly. So 8 times the reaction 1 plus 8 times the reverse of reaction 2. And if we actually do that, this would be reaction in part B. And now we have information about reaction 1 and reaction 2. So then we can, and we know how to combine it based on chapter 1. Then K overall, which is not E0 of the reaction because this redox reaction is not standard. Then it would be the K value of reaction, the first reaction, which is equal to E0 to the power of 8 times 1 over of the K value of the other reaction. And this would be 10 to the minus 13.73 to the minus 20.78. 10 to the power of 56.40. And this is 56.40. And as you can see, this is obviously not equal to simply adding the PE zeros. Because this reaction is not a standard reaction again. Yep.
The first reaction you wrote the oxidation state of chlorine. Instead of you take the sulfur, it will be the oxidation.
What is it? Sorry. Mm-hmm.
Then you check for the chlorine's oxidation state.
Okay, yep.
Instead, if you check for the sulfur, it will be the oxidation reaction.
So for the sulfate, it would be a little bit more, if you remember, we had a general rule of going for oxygen always -2, for example. But then sometimes there are some, yep. So it's easier to go with Cl-. I'll double check this example. I'm 90% sure, but I'll double check this one to see.
But chlorine's oxidation state has reduced, right? Plus 1 to minus 1.
So it's reduced. Yeah.
Generally, the reduction in oxidation number is
So oxidation reduction is reducing the oxidation state.
yes. So plus 1 to minus 1 is reduction.
Yes.
We have considered it in oxidation.
No, it's reduction.
Oh, okay.
Yeah, no worries. So I need to double check this example. It's a little bit I have to double check this one. But I'm 90% sure that this is what we got. So let's just wrap up to what we talked about so far. We did 2 out of 4 what we were expecting. Always standard condition, first half reaction, and now combined reaction, which is the redox reaction. But the point is, we're not always at the standard condition. The non-standard condition represent most of the cases. But we need to know how to use the information in the standard condition to describe non-standard condition. And we did that before for Gibbs free energy, for example. We have Gibbs free energy at standard condition coming from tables, and then we drive some relationship to use that information, talk about deviation from non-standard condition, to talk about delta G at non-standard condition as well. So here would be basically the same. We're going to describe electron activity at non-standard condition for both first half reaction and then the overall redox reaction. And then it would be very similar, logically it would be similar to what we did for delta G. It's basically what's the deviation from non-standard condition. And if we can do that, that'd be very powerful, because we can describe the electron activity at any condition for any redox reaction. And that's basically the whole idea of Nernst equation, probably the most important relationship in electrochemistry as well. Here we're approaching it from the electron activity, but it would be basically the same thing. So first let's focus on the half reaction and see what would happen if we have a half reaction, the deviation from the standard condition. So let's assume, again, this general standard reaction of 1 over n of reduce going to 1 over n oxidize plus electron. We know the K value for this case because it's written in the standard notation. It would be equal to E0. Then the oxidation over 1 over n electron, and then the reduced species 1 over n. Now we can do minus log of both sides. Then it would be P E0 equal to minus log of that whole thing. Oxidation 1 over n and reduced form 1 over n, and then the activity of electron. And now we can apply this function to the individual parts. So basically this would be equal to minus log of oxidation species 1 over n, the reduced species 1 over n, minus log of activity of electron. What is this term? This one. PE. So the activity of electron at any condition. But this one is the activity of electron at the standard condition. So we can also play with the log function a little bit. So this would be basically PE. So we can bring out that 1 over n from the log. And then this would be ox over reduce plus P. Or we can rearrange it to say PE is equal to PE0 plus, minus 1 over n log of the reduced species over the oxidized species. And this is basically called Nernst equation. So this relationship is extremely important because it's talking about the activity of electron at any condition as a function of deviation from the activity of electron at standard condition. So this is for half reaction. If, again, you took electrochemistry in the past, this form is basically E and E0 minus 1 over N and then some Faraday constant sort of factor. This would be basically the same thing. Again, approaching it from a different angle. So the Nernst equation is one of the fundamental equations of redox analysis. As I mentioned, if not the most important, it's one of the most important relationships that we have for redox reaction. So what it says is basically it determines the PE, activity of electron, in a solution at equilibrium based on speciation of a redox couple, or it determines the equilibrium speciation of a redox couple in a solution with the activity of electron. So, for example, if we know what's the activity of electron in this solution, and if you add some redox species, then that activity of electron would dictate the speciation between the two. Or if you added the speciation, it would eventually dictate the activity of electron. So basically, if we have the simple form of PE0, 1n log of reduce, just keep in mind this is log of reduce over oxidize, and 1 minus 1 over n. You could have like plus, but then you have to switch these two. But in the form that we wrote, it's reduce and then over oxidize. So in this formula, this is the activity of electron at non-standard conditions. This is basically activity of electron at standard condition. And this is basically what can be modulated by changing the activity of electron. Or this ratio would dictate the activity of electron eventually. The ratio of the reduced species over oxidized species. So again, we use this in electrochemistry a lot. You look at the table and you find, let's say, the reduction potential of copper to be 0.34, for example. But that's measured for a standard condition. For example, you had 1 mole of copper in the solution, it was 25. But then you go to the lab and then you have a different concentration of copper. Then you do this adjustment based on the new non-standard condition by putting stuff in this reaction, in this equation. So that's a very useful tool. So now we did it for half reaction, the same thing we do for a redox reaction. So basically a Nernst equation for a redox reaction. So this would be also pretty straightforward. What we showed so far at standard condition, we have PE0 of reaction equal to PE0 of oxidation minus PE0 of reduction. So that's what we showed in the previous case. So let's, let's move this for now. maybe it's too soon to talk about this. So first, let's assume the same reaction we have. So the same reaction as in page 2. So that A, B, C, D with 1 over N, 1 over. So this reaction was in terms of the oxidation. This was 1 over N1A forming 1 over N1B plus electron. And this would be E0 of oxidation at the standard condition. We can also have E0, not E0, E of oxidation at non-standard, using the formula from the previous page, basically. We also had reduction to be 1 over N2C, again in the standard format, 1 over N2D plus electron. Then this was E of reduction, and for the non-standard condition, this would be just E. But now we are interested to look at the overall reaction. The overall reaction would be 1 over N1A. Again, very similar to what we had. Not very similar, it's the same as what we had in page 2. So for this reaction, what we showed was that PE0, so this would be basically E0 of reaction, or E0, E of reaction at non-standard. Now we want to calculate what would be this value. So basically that's the whole point of this part. Because we already know this two, we just calculated these two. We show how this is related to these two, but now we want to just calculate this guy. So we show at the standard condition, this would be the case. We can also show that this is also true for non-standard condition. So at non-standard condition, also the reaction would be PE0, PE of oxidation minus reduction. This is what we need to calculate. How do we calculate these two? Exactly. From the Nernst equation we just had for the half reaction. So this is basically these two from the Nernst equation for half reaction. So now we can basically expand this a little bit. PE of reaction would be the Nernst equation for oxidation, which was PE0 of oxidation minus 1 over n1 log of the reduced species, which was A over B. So this would be minus PE0 of reduction minus 1 over n2 log, in that case it was C over D. This is basically PE of oxidation we expanded. This is PE of reduction. So now we can do a little bit of rearrangement to hoping that we get something more familiar out of this A, B, C, and D. So first let's combine these two, because we already know if we combine these two what we would get. And then let's combine these part to see if this is something familiar. So combining the first two, as you might guess, PE of reaction would be PE0 of oxidation minus PE0 of reduction minus 1 over N1 log of A over B minus 1 over N2 log of C over D. What is this part? For reaction, so PE0 of reaction. Something that we can find from tables by looking at tables for oxidation and reduction at the standard condition. So now let's work on the second part to see if we can basically get something familiar out of that. So PE0 of reaction minus, let's combine all of them together, log A 1 over N1 D 1 over N2 C or is this familiar? It's what? Somehow similar to K, but this is not standard condition, so this would be somehow similar to Q. Is it Q or is it something else based on the reaction we had in the previous page? It's 1 over Q, exactly. So it's inverse of the Q factor. So this would be basically this part, 1 over Q. So eventually what we get is PE of reaction equal to PE0 of reaction plus log of Q. Wait, work. And this would be the Nernst equation for the redox reaction. Again, similar to the previous case, is a deviation from the standard condition. Exactly identical as we had for delta G. Delta G was also a deviation based on Q with some RT, I guess, and then delta G of 0, and to get to delta G of the reaction. So again, this is a very useful tool to have we can calculate the electron activity of a redox reaction at any condition. And now we're going to basically use it. So before we calculate for some examples, let's also connect this E0 and E to something that is also very useful, and that's basically delta G. So we want to calculate the molar Gibbs energy for a redox reaction as a factor of what we had in this lecture. So to connect it to PE or PE0. So we already know that based on chapter 1, delta G at the standard condition, this would be equal to minus RT ln K. And for a standard reaction, for a redox reaction, then that K value would be basically E0. So that would be minus RT ln E0 of reaction. So this is basically true for a redox reaction. Or let's make it log, not natural log, then this would be equal to minus 2.303 RT log of E0 of reaction. Or we can make it in P form, so delta G 0 of reaction would be 2.303 RT PE0 of reaction. Again, this is also very useful because you can calculate delta G for a redox reaction at the standard condition. By looking at tables, figuring out what's E0 for oxidation, what is for reduction, then oxidation minus reduction to get to that reaction. And then this would be pretty straightforward. It's temperature dependent as we had in chapter 1. But now we can do delta G for also a given reaction at non-standard condition, like what we had before. So we had delta G R at non-standard condition to be delta G R0 plus RT ln Q. That's what we had before. And now we can replace it by 2.303 RT PE0 of reaction from just what we had now, and then 2.303 RT ln, not ln, log Q, just converting ln to log. We can now rearrange it a little bit. Then this would be 2.303 RT PE0 of reaction plus log Q. And as you can guess, this is basically equal to this guy. 2.303 RT PE0 of reaction. Up. So we get delta GR for reaction to be 2.303 RT PE of reaction. So now we have sort of a triangle. Before we had delta G, or we could connect it to K, And now we have also delta GR connected to K, also connected to E. And then we know how to go back and forth between these factors. Delta G and E would be this formula. Delta G and K, delta G0 would be this one. And then we can basically go between these two, which would be in this case the same. So we try to use something that is very important for a redox reaction, which is delta G, and then connecting it to something that we described in this lecture. And similar to other reaction, for a process to be spontaneous, for a spontaneous reaction, delta G R was negative. So that means PE0 or PE reaction must be also negative. So that's for a spontaneous reaction. If it's at the standard condition, obviously PE0 must be negative. So now let's work on two examples. This is the first example is a very straightforward, and then this is extremely useful, specifically when it comes to, for example, corrosion. The question is asking whether copper plus can reduce lead 4+. In this case, it's asking about standard condition, but probably in the exam you have a non-standard condition. It would be the same approach. Here you're dealing with delta G R of 0. In the exam, probably because it's a non-standard, you have to work with delta G R. So here, for the sake of simplicity, we have a standard condition. So the question is, can copper plus reduce lead 4+? The only information that is given is obviously PEs and then PE0 for a given redox. Here, we don't need to identify what is oxidized, what is reduced. It's actually given. So can copper reduce Pb4+? That means copper has to oxidize, right, to reduce Pb2+. So the oxidation reaction would be copper plus to what exactly? Copper 2+. Why is that? Why not, for example, and this is very imaginary, why not copper 3+? I know it doesn't exist, but based on the intuition, of course. But here also it's given, the pair is given here. So sometimes it might be more complex, like chromium specifically. We don't know chromium 2+ could oxidize to, chromium 1+ could oxidize to 2, but also could oxidize to 3. But then we have to look at what is given. So in this case, copper 2+ plus electron. And then for this specific reaction, it's already in the standard state, in the standard notation. It's releasing only one electron in the oxidation. So E0 would be E0 of copper 2+ copper plus, which is 10 to the minus 2.69. Let's put it this one. So the next one is basically reduction. It's Pb4 plus it's forming basically Pb2 plus, again, because of this guy here. And we know to balance this, we need 2 electrons. No information about this reaction, rather we need to make it in the standard form. So half of Pb2 plus forming half of Pb4 plus electron. Now the standard reaction for this one would be Pb4 plus Pb2 plus 10 to the minus 28.64. So normally I should give you these two values in the form that one is oxidized to the other guy. but don't rely on that. Sometimes I'm lazy and I just switch to this too. So, and also it's your job to calculate the oxidation state to figure out what is what. So now we can also write the overall reaction, which is basically reaction 1 plus reverse of reaction 2. So copper plus half of Pb4 plus, copper 2 plus half of Pb2 plus. And this would be 0 of the reaction. Just to double check, the overall reaction says whether copper can oxidize Pb4 plus. Because copper is whether copper can reduce Pb4 plus. So that means copper has to be oxidized and Pb4 plus has to be reduced, which is the case for this specific reaction. So this is a combination of two standards, so we can quickly calculate PE0 of reaction to be PE0 of oxidation minus PE0 of reduction, or 2.69 minus 28.64, and this is minus 25.95. So back to the question, can copper plus reduce Pb4 plus at standard condition? So PE0 of reaction is negative. That means delta GR, in this case at the standard condition, is also negative. So this is spontaneous. So again, this is at standard condition, very specific condition, but you could actually calculate for non-standard condition and see whether delta G is eventually negative or positive. And as you can see, by changing the concentration of copper plus or Pb4 plus, you can also change the direction of the reaction to go from a non-spontaneous to spontaneous, or vice versa. Okay, so the last example is a little bit more comprehensive. It's asking us to look at two half reactions and then combining them together to get to the overall reaction. The pH is given, the concentrations or activities are given. So that means we are at non-standard condition. And it's asking us to calculate the, I think, delta G of the reaction. Yep. Estimate the molar Gibbs free energy for a reaction that HOCl is reduced to Cl minus. So it's also given what is reduced, what is oxidized. So the pathway is obviously we calculate E0 of reaction, then E of reaction, and then connecting E of reaction to delta G of reaction. So basically a combination. And on the way, we need to do Nernst equation for both, for half reaction and redox reaction, because this is non-standard. So take your time, read this statement just for 30 seconds, and then we go back to it. So all the information is given. So we have these 4 species in the solution. We just want to see what's the delta G of reaction if HOCl is reduced to Cl minus, and the H2S is oxidized to sulfate. So we know what is the oxidation reaction. It's already given, H2S. We just need to balance it. Plus 4 water would give us SO4 2 minus plus proton plus electron. We need to make it standard, so then would be 1/8 of H2S plus 1/2 of H2O, 1/8 of SO4 2 minus, and then 5/4 of proton plus electron. Then this would be E0 of oxidation, also E of oxidation, depending on what we need to calculate. Going from here to here would be basically a Nernst equation for half reaction. The reduction is also, we have a hint of what is the reduction. We know HOCl is involved, also Cl minus. So when we balance this reaction, we get something like this. We need to make it standard, so half Cl minus, half water would give us half HOCl plus half proton plus electron. Then we get E0 of reduction and E of reduction. Now we can write down the overall reaction. This is basically 1/8 of H2S plus half of HOCl, forming sulfate, plus Cl minus, plus proton. Because proton is involved, that's why pH is given. So now we have basically everything to calculate PE of reaction, because once we have PE of reaction, then delta G of reaction would be pretty straightforward. So we know PE of reaction is equal to PE0 of reaction plus log of Q, so the Nernst equation. We also know PE0 of reaction is PE0 of oxidation plus PE0, actually minus, of reduction. We already have that. And we also know Q is, in this case, sulfate 1/8 Cl minus and proton and H2S HOCl. And we basically have values for all these activities. It's all given. So if we combine these three, I'm going to skip the calculation. Then we get PE of reaction to be minus 24.89. So we know how delta G of reaction is connected to PE of reaction. So this would be 2.303 or T PE of reaction. Just be careful with the unit conversion a little bit if needed. R is 8.314 joule mole Kelvin. Temperature 25, so it's 298 Kelvin. And the PE value, minus 24.89, minus 142 kilojoule per mole. So to wrap up what we've learned in this lecture, we first talked about half reaction. For half reaction, we knew how to go from PE0 of aux or reduced to PE at non-standard condition. So using the Nernst equation, we also did this for a redox reaction, which is a combination of the two. How to go from PE0 of reaction, which is basically PE0 of aux minus PE0 of reduced, to go for PE of reaction, and then how to go for delta G of reaction. And then this one we could also calculate delta G of reaction at the standard condition. And based on the sign of delta G, which is related to the sign of PE, we were able to see whether a reaction, a redox reaction, is spontaneous or not. Any question? Okay, if not, in the next lecture, so what we did so far in this chapter was the first one was introductory, balancing the reaction a little bit. This one we focus more on the PE, specifically the PE. In the next lecture, in the next two lectures, we're focusing on graphs. So how the concentration of species would change if we change the activity of electron, similar to PC-pH diagram. This time we can manipulate the E. In the last lecture, it would be PE-pH. So this would be a very fun lecture. It's basically a Pourbaix diagram eventually. How the pH would change the activity of electron. And later, you know how activity of electron is changing the activity of individual species. So it would be a 3D diagram kind of thing. And then that would be the end of chapter 4.